Assalamu alaikum students. Today we are going to learn about maximum likelihood method. In the last lecture we learned about method of least square. This method was proposed by Sir Ronald A. Fisher. The logic behind the principle is that to consider every possible value that the parameter might have, and for each value compute the probability that the given sample would have occurred. If that were the true value of the parameter, the value of the parameter for which the probability is of the given sample is greatest is chosen and estimate. Estimates obtained by this method are called maximum likelihood estimates. The maximum likelihood estimates are consistent, efficient, sufficient, but not necessarily unbiased. This method is applicable for discrete data and also for continuous data. There is some other definition for maximum likelihood. The likelihood function indicates how likely the observed sample is a function of possible parameter. So, likelihood function f of x is the joint distribution, is also called joint distribution. Joint distribution of parameters, joint distribution for samples. There is a slight difference between likelihood function and joint distribution. Likelihood function is supposed to be the function of parameters, but the joint distribution is supposed to be the function of samples. When we multiplied the function for each value of the sample, say x1, x2, x2, so on, xn, and we multiplied the functions by putting these values in the function, and the obtained multiplied result is called joint distribution. Therefore, maximizing the likelihood function determines the parameters that are most likely to produce the observed data. From statistical point of view, MLE, MLE maximum likelihood estimates is usually recommended for large samples. For small samples, you can use least square estimates, okay, because it is versatile, applicable to most models and different types of data and produce the most precise estimate. Now the some are important points here I have formulated for you. Maximum likelihood estimates are unbiased. Maximum likelihood estimates for standard error are biased. Maximum likelihood estimates are good for large samples. Here are some other properties in the last slides, that the maximum likelihood estimates are consistent, efficient, sufficient, but not unbiased. And these properties can be used to formulate MCQs in your paper. So do not take them lightly, uh, because your paper is based on these short questions and MCQ. Now, here in this topic, we are going to estimate the parameters of the simple linear regression model using the maximum likelihood method. So, we will start from the model we already know. Y is equal to a plus bxi plus ei, which is the simple linear regression model. In the second step, we take out of the equation error, and the rest of the model is written here y minus a minus bxi, because this part of the equation is shifted here, and the signs will be negative. The probability density function for normal distribution is that. I think you already know about the normal distribution function. So, uh, for variable x, there is x minus x bar. We use here variable ei. You can see that ei. For ei, we have to put there ei and e bar. We already know that summation ei is equal to 0. So, since the mean of the random error is 0, so we put 0 over here and we will get the result here. Now, there is EI. Now, this is the normal distribution function for errors. Now, the joint distribution of f of x for the sample for x1, x2, and xn, we have this. We multiplied all the. So, this is the joint distribution, also called the likelihood function. If you want to learn more about the joint distribution and likelihood function, so you have to consult the statistics books from Sherman Chaudhary, basic statistics. There is a whole chapter for this maximum likelihood method and least square method and method of movements. So, by multiplying these values, this this part is constant, and that's why we take power n over 2, because there is under root, and we multiplied 2 here and divided by 2 here, so no need to worry, these two can be cancelled out, but the requirement is here is we need sigma square over here, because we have sigma square over here. So, this portion is not a constant, this is a variable over here, and this is called summation x1, summation x2, and so on. So, the powers will be added because the exponent is same. So, we take summation ei square. Now, by taking log on both sides, we got this. The basic purpose of taking log is that this is a complex function. This one is a complex function. We cannot take derivative so easily. So when we take log, you can see that this term is separated, this term is separated, and this term is separated by taking minus. So it is easy to take derivative of this function instead of this one. Okay. Uh, Now put ei is equal to y minus a minus bi, which is the second equation in the previous slide. Over here, over here, we have to put ei, this ei over here. So we got to this, we came to this result. Now this likelihood function is ready, uh, and we can take partial derivative with respect to a, with respect to b, and with respect to sigma square. So now if we take derivative with respect to a and with respect to b, and solving the two equations, we came to these values. Uh, these are called the normal equations, which you already know from the least square method. These are the normal equation methods. Solving these normal equations by using the cross multiplication method, I also previously told, and you already know what is the cross multiplication method. We came to the following results. Now you can see that these results are the same as compared to least square estimates. Now, taking derivative with respect to sigma square. Now, there is sigma square and there is sigma square. I do not need to tell you how to take derivative because you already know about the derivative. Now, log of sigma square. The derivative of log of sigma square is equal to 1 over sigma square. This one here. And we have already sigma square. Now, the derivative of this will leads to minus 1 over sigma square whole square. Now, there is a point that we are taking derivative with respect to sigma square, not sigma. That is why we do not take the power this. Now, sigma square is the variable, not sigma. Okay. Now, putting this equation equal to 0 and solving it simultaneously, we came to this result because this one here is E equal to E. In the previous slide, I told. Now, this is the estimate for sigma square. And that's all for today. Thank you.